The format of the evening is the usual one, that in a few moments' time John Fraser will give us a talk about the night sky, and that'll be about 15 minutes, and then after that Jerry will introduce tonight's guest speaker. Before we do that, just the usual housekeeping messages to give you. If the fire alarm goes off, please leave the building safely by the doors each side, gather on the car park, and we'll check everybody is safe and sound. Toilets just outside the door opposite where Tony was sitting. And if you've got a mobile phone, if you could turn it to silent or sleep or whatever you're meant to do, so it doesn't interrupt the meeting, that will be very welcomed. For those of you on Zoom, it's lovely to see you here as well. And the main thing we ask you to do is please keep your hands away from the space bar, otherwise you might join the meeting with some words that we weren't expecting. After our speakers, there's the opportunity to ask questions. Those of you in the room, you can put your hand up. We'll bring a microphone to you. That's important so that the people on Zoom will be able to hear you. Those of you on Zoom could submit your questions by using the chat facility. So,
thank you. Okay, so this is Night Sky News. I quickly take you through what you can see in the night sky, what happened last month, what might happen this month. Okay, so I always like to start with an introduction to the night sky for people who are still learning their way around. I've got to say, I actually really count myself in that number as one of the people who find the way around. Okay, so this is Cassiopeia, or Cassiopeia, I'm never quite sure how you pronounce it. The big W in the sky, she was the mother of Andromeda. Andromeda is just off the bottom of the screen here, and we'll come back to that. It's one of the more recognisable constellations in the sky. I say it's the W, I always think it was a W, but of course as the sky rotates, it can be an M, it can be a 3, it can be an E. This one here was pointed out to me by the gentleman at the back. This is the Bluetooth constellation. Okay, so it's almost unseeable in from. Oh yeah. Right, I'll describe this. To find Cassiopeia, you start with Ursa Major, which I talked about last month. Starting off with the plough, if you follow it along to the next reasonably bright star, you're in Ursa Minor, and you're at Polaris, and then carry on for about the same distance and you get to the W of Cassiopeia. The 4 stars on this side of it, as I'm showing it, these are magnitude 2 to 3, so they are pretty bright. This one's a bit dimmer, it's 3 to 4. But you can see this even in a pretty light polluted sky. And it's one of the few constellations that I'm able to pick out in a dark sky. Sometimes it's very hard to see the constellation in a dark sky, but this one's quite distinctive. Okay, I like to point out some of the things you can find around the constellation. I usually go for Messier objects because when he was making his catalogue, he had a very low powered telescope by today's standards, so you can pretty much find these if you're in a dark enough sky. Of course, M31, it's M31, isn't it? Yeah, M31, the great galaxy in Andromeda, just down below it. The larger part of the V points at it, about 4 times the length of that line will take you to Andromeda. And M103, which is, I don't know what's happened there, it's actually moved it, it's on the other side of this line, and it was last time I looked at this. Okay, so it's actually slightly over this side of the line. This actually was the last object that Messier put in his catalogue. There are 110, yeah, oh sorry, there are 110, but the last 7, although you observe them, they were added to the catalogue much later. Okay, so the moon. The moon is full tonight, doesn't matter, it's cloudy and we're here, and it buzzes several of the planets and gets very close to Antares. Okay, and it's going to hit just before, I think, the next meeting. So Mercury, Venus, Saturn and Neptune are, it's not my mistake, I haven't put Neptune up there. Neptune should be just about there, I think. These are together in the sky, part of the supposed grand parade. Mercury is moving away from the sun at the moment, so these appear at sunset. Mercury's moving away from the sun. It's going to do that for the next week or two before it starts heading back in. This picture is taken on the 12th of March, or image is taken from the 12th of March. Saturn and Mercury are about 1.5 degrees apart. Saturn's going the opposite direction. Saturn's sinking in the sky, and it's setting earlier each evening. It's going to go around the back of the sun fairly soon. It's dropped in magnitude to 1.14, whereas Mercury is quite bright for that at 0.36. Okay, so Saturn's going away. We're going to lose it in about 6 weeks. Venus is incredibly bright at the moment. It hit January on Valentine's Day, happily enough. And it's going to start. Thing with Mercury, I always say this, do not look at it while the sun is in the sky, not through binoculars or not through a telescope. Really, really dangerous thing to do. Okay. Anyway, Mercury will carry on moving up until it has a close encounter with Venus on the 6th of March, where it's about 6 degrees apart. Which probably be about the best time to see it if you're looking out for it, because Venus won't quite be as bright as minus 4.64, but it'll still be the brightest thing after the sun and the moon. So you'll be able to pick out Mercury there very easily. Mars is lurking around in Gemini, in the Twins, appearing at sunset. It's pretty bright. It's about 0, slightly better than 0, but not much. It's currently in retrograde motion, where the Earth is catching up with it, so it appears to reverse its direction in the sky. 24th of February, it will stand still for the night, and then it will start going in the normal direction. And even though people keep telling me, I can never remember which is the normal direction, but it will reverse direction. All right, and this is 1.5 degrees apart. This is at midnight on the 9th and 10th of March, between 9th and 10th, 1.5 degrees apart. That's about 3 times the width of the full moon. So, finally, Jupiter's sitting in Taurus and will be for a while. It's slowly going to head up in this direction. Very bright, minus 243, so it's the brightest thing after. Uranus is down here, still hanging around below the Pleiades. And it's going to be about 5 degrees from the moon on the 5th of February. It's already passed, so I don't know why I put that there. It's probably a reason. Okay. So this is what happened in the last month. So this actually didn't happen in the last month. I actually think it happened in December, a wooden satellite. But I read about it this month, and I thought it was quite amusing. So JAXA sent a wooden satellite up to the ISS, and they tested it. For thermal properties, strength, insulation. The reason for a wooden satellite is when a satellite re-enters, it burns up. Now, a wooden satellite, in theory, would completely burn up, whereas metal satellites, because of the way they burn up, can leave particles of themselves in orbit for a while more, which is quite risky to other satellites. Gaia was a satellite released by ESA. It's been sitting out in L2, had James Webb for a company for a bit, and it's been observing about 1 billion stars, nebula, various objects in the sky, got them to very high precision. A lot of papers have come off the back of Gaia. It essentially ran out of fuel. So Starship, you probably saw on the news, it took off. They caught the first section, so this was test 7. The top section, the actual orbital part of it, blew up shortly thereafter. New Glenn was almost the opposite. Now, New Glenn isn't a test. New Glenn is a fully functioning rocket. Got to orbit on its first launch. Not everything does that. I think Ariane 4 or 5 blew up on its first launch. So it went up. It had a payload of, I think it was called Blue Ring, which was a satellite platform stroke tug that they used as the test vehicle, but this is fully functional now. Unfortunately, it was the opposite of Starship, because the top section made it to orbit, but the bottom section, which is reusable, wasn't recovered. So both of these two are now completing accident reports for the FAA. So they got to do that before they'll be allowed another launch. This is one of my favourite new telescopes, the Vera C. Rubin telescope. It was the Large Synoptic Survey telescope, which is going to map galaxies out to billions of light years, take large sections of the sky, picture the large sections of the sky over 6 years, and the idea is to map where the dark matter and the dark energy is. They tested it with a test camera. It has the largest digital camera, 3.2 gigapixels. That's going to get hooked up over the next year. Right, OSIRIS-REx, the samples it returned from the Bennu asteroid, they published some of the results. It had 14 of the 20 amino acids that are used by life on Earth, or life as we know it. All 5 of the bases used in RNA and DNA were found on there. And somewhere, if you listen carefully, you can hear Fred Hoyle cheering. Okay, so this did make the news as well, this asteroid. This asteroid has a 2.3% chance of hitting the Earth. Now, it comes around every 4 years. It's definitely not going to hit it in 2028. But there is a danger, 2.3% danger. It will intersect with the Earth's orbit on the 22nd of December 2032. Now, the Torino scale is a way of measuring the danger that asteroids present to Earth. This is the Torino scale. This is 3 here. So you can see it's a long way from being considered dangerous. It's basically keep an eye on it and find out more stuff. Nothing's ever gone above a 4. Normally they come in at a 2 or a 3. Well, normally they come in at a 0 because there's no risk. But the ones that get above that go here, they get more observations, it moves down. So it crosses the Earth's orbit. There is a 16-minute window where if it crosses at that point, it'll intersect with the Earth while the Earth's there, and it'll intersect here. So if you're booking a holiday in 2032, you might want to consider not being on this line. Right, the asteroid's about somewhere between 40 and 100 meters across. Every time I practice this, I said kilometers, which would be scary. It's meters across. So I couldn't find anyone who gave reasonably accurate estimate of the damage, but it's in the megaton range. Unfortunately, it's not a very reflective asteroid, so it's very difficult to work out the size. It's also very difficult to accurately work out the orbital, accurately enough. So if it hits the ocean or it hits wasteland, it probably won't be too bad. If it hits a city, it's going to drop the house prices very, very fast. But there should be enough time in a sane world, and hopefully we'll be in a sane world again by then, to evacuate. And we had the DART mission, which did show in theory we can deflect asteroids. Although, want to pay for it, look at the countries on that line. Okay, so what we got this month? So this month, Ariane 6 is going to do its second launch. It's the ESA heavy launch vehicle, the Ariane 5 launch, JWST. It's doing a French spy satellite this time. So there's 2 missions are going to be launched to the moon at the end of the month. No, is it? Yes, launched to the moon. First one's Intuitive Machines. Their first lander, this is their second lander. Their first lander, if you remember last year, it toppled over on its side, worked for a few weeks. I think it made it through the first lunar night. So they're giving it another go. The second one is called, I can't see my notes, Trailblazer, which is going to orbit the moon. Both of them are supporting the Artemis missions. Blue Ghost, which is launching on the 2nd of March, is also there to support the Artemis missions. They're doing a lot of experiments. One of the ones they all seem to have in common is they're looking for water, because of course water is a major reason to go back to the moon. And we got the total eclipse at the end of the month. Now, The astrophotography section have been brilliant and busy. So we don't get many of the moon. In fact, this is, I think, the first one. So this one's from Martin. Really nice picture of the moon. I really like this one. When I first used the telescope, I pretty much only looked at the moon because it was all it was good for, but I spent many, many hours wandering around the moon. I love this picture. It's great. I was going to say this is where Apollo 14, and I thought I better not do it to this audience because I'll get it wrong. Okay. So, Mikhail, wonderful picture of Jupiter. I've got to say, in the studio, this is not doing it justice. On my computer screen, it looks even better. He did several really, really good pictures of Jupiter. I picked this one out, particularly because we've got one of the satellites. I don't know which. I'll say Ganymede. Got 1 in 4 chances, right? Up here, we've got this white dot in the northern temperate band, which is the outbreak, I think, of a storm starting there. So I think it's a great picture for showing how dynamic that planet is. Peter Goodhue, another amazing, absolutely amazing planetary nebula. This thing is 183 arc seconds across, which is roughly, by my calculations, a tenth of your little tip of your little finger held at arm's length. It's absolutely incredible. To be honest, I can't even find this in the sky where it is. I think there's something like 180 hours of imaging went into this. It's a planetary nebula, which are how stars like our sun will end their life when they move into the stage where they're burning helium. This one, to my knowledge, is fairly unusual. The light curve, the way it drops, shows that the stars in the centre of this is actually a double star. Great picture. This one's from Steve. Great picture of Mars. Nice polar ice cap showing, which I believe is mainly carbon dioxide. I did try to work out what this feature was. Do you happen to know? No, good. Wasn't just me, but brilliant. Yeah, Mars. It's a great picture. We don't get many planets. I think they find them too easy. So this is, again from Martin, Thor's helmet. This is a emission nebula, and I am going to have to look at my notes because I keep getting this wrong. This is about 12,000 light years from Earth, and it's about 30 light years across. The thing's being lit up by a Wolf-Rayet star towards the centre. Wolf-Rayet stars are stars, incredibly energetic, incredibly bright stars that are imminently, in astronomical terms imminently, going to the supernova stage. Oh, I'd love that. That's a piece of art. This one sits just here, so close to Sirius, just off Canis Major, the great dog. So another one from Steve, the jellyfish nebula. I think I showed a picture of this a different picture completely. I think it was Martin's picture last month. Sorry if it isn't. This is a supernova remnant. Blew up about 30,000 years ago, and I think it's about 5,000 light years from the Earth. There's a pulsar at the centre, which means it's almost certainly a type 2 supernova that caused this. It's very, very well studied because in places it's colliding with the molecular clouds in the Milky Way. So this one has been studied an awful lot. Okay, finally, so this is where it sits, just off Gemini, or just in Gemini, down one of the legs. So last month was the Hertford Dark Sky event, which I managed to miss again. Although this time it looks like they got the weather for it, because that's, mind you, dark skies, you're wondering what was all of this about? They're the only place that didn't get the message. Great picture, you got Orion there. You got Mars sitting there between Pollux and Castor. You've got Jupiter, I think, just about there. So really, really nice sky. There was a good turnout by the look of it by the group. The usual suspects. well done, seriously. And there was an inside picture, they had an inside display as well. So well done to them for doing this. Anyway, that's it. Any questions?
John, that was a brilliant presentation.
Thank you.
Do you produce a crib sheet with this?
Right. Last month I said that we were going to start putting these up on the website, and then I promptly went on holiday and never sent it to Alan. I will send this off to Alan. It may just be a PowerPoint presentation with my notes to one side, but yes, that's the best we do.
I will say that was absolutely wonderful.
Well, thank you.
Not inspired by that, you've lost your soul.
I've got to say the astrophotography group, which I'm not part of, they produce pictures better than I used to see out of professional telescopes when I started. I mean, unbelievably great, these guys.
Do we have any more questions? Obviously spellbound by your presentation. Can I say thank you very much indeed, John, and echo those words. And thank you to everyone who contributed towards that. Thank you. Jerry, over to you.
Just something to add on to that. Alan, are you going to say something about the Eclipse watch later? Okay, fine. I don't need to do anything just now. Right. I'm very pleased that our speaker this month is someone that I've known from the RAS for many years, Quentin Stanley, who's here with his wife Liz, having made a journey around the M25, which is a fair task in itself. You can see really the details of what Stephen has done on the website, but the RAS monthly meetings are followed by a grand dinner for the hoi polloi. Stephen organises the RAS alternative dinner, and we had a superb one in December at a restaurant near Piccadilly Circus, where it was a real restaurant, not one that decorates plates with bits of food, but actually serves up a proper meal. He also organises the RAS annual picnic, which we hold in Greenwich Park in the summer each year, on pretty much what Google Maps marks as the meridian, because of the model that they use for the Earth, when in fact it's not the meridian, it's a couple of 100 yards from the real thing, but we don't mind really, and we have a really good time. His subject tonight is the art of computer modelling. Don't get worried. It's not going to be a huge technical academic discussion, is it? Please welcome Quentin Stanley.
Okay, super. Well, thank you very much. I know, sort of like Jerry invited me here, and it's a great honour to be here. And as we say, if anyone can, Jerry can. So there we go. But anyway, it's lovely, and I've heard good things about you, and I will say it's a real delight to be amongst people who take real good interest in astronomy and really take a passion in what they do and produce. As we just saw some fantastic images, a fantastic crib sheet from John, and please, use that, and I'm certain you will support each other very well. Anyway, the art of numerical modelling is what we're talking about. Now, you'll probably have speakers here and wherever you go, and you'll hear that phrase, "it fits our models." And you'll be saying, oh, right, okay, it fits our model. For instance, Wolf-Rayet stars, as you're talking about there, John, and they're talking about sort of going supernova or whatever. How do you know? What's the modelling? They talk about this. They talk about dark energy. It fits our models. They've modelled the origins of the universe and the inflation. It fits our models. And you're thinking, well, okay, it fits your models, but you're not really explaining it. And if you don't really understand what's going on sometimes, you don't know quite what questions to ask. So what I'm going to do here is I'll just take you through a little bit of how numerical modelling works, give you a few little examples, and this is just to give you an idea, and you can take this home and do it yourself at home. So what I'll do is to start with a little bit on this one, and we'll sort of start off with model of the glen. That's art, and we can see that very, very famous piece of artwork by Sir Edwin Landseer. See it on a whiskey bottle, always good to see that there, and if you've drunk enough whiskey you won't see it again. Mona Lisa, you know Mona Lisa. You spot these things, you analyse these things. Very recognisable. Cheers. We've got here also, this is an interesting one. 3 female musicians. This is actually done by Master of the Female Half-Lengths. It was a group of people, not actually known, and this was painted in the 16th century, something like that. But you recognise it as 3 women playing instruments. This is also 3 people playing instruments by Pablo Picasso. But you sort of, once you know it, you recognise it. But this is the thing with numerical modelling. You can get it very wrong. But sometimes it gives you a little bit more than you were expecting. So there we are, Pablo Picasso. But with numerical modelling, you can do other things. You can sort of left field. This is, persistence of memory, Salvador Dali, the melting clocks. We all know this one as well. Then you can sort of say, well, with modelling, we can also sort of image things without experiencing. You've got the great wave, the tsunami of Hokusai. That isn't the real wave. That's an image of a wave actually done in pen and ink, and it sort of gives you the impression. And numerical modelling gives you impression. You don't have to be there. You don't have to actually get wet, and you don't have to actually scream at seeing a wave coming at you. You can actually just sort of think about it and thinking, I'm glad I'm not there, which is quite the. But again, it can go quite wrong. If your numerical modelling is not really adjusted to the physics of what you're thinking about, you could do, so if I can go back one, I just went there, you end up with this. The stairs are going in the different directions. It looks right, but actually it isn't right. And you have to be very careful when you're doing your numerical modelling that when you come up with the result is real. You can lead yourself astray, and it's very easy to lead yourself astray. So you have to be careful. Now this one, this is Artemisia Gentileschi. This is painted in, I think it was 1638. And what is she painting? She's painting herself. Painting herself, which will be painting herself and painting herself, painting herself. Now, she'll play a little part in the story a little bit further on. But this is sort of this recursive attribute of one painting, and this one is based on the other, on the other, and the other, and it's just a repeat. So we bear her in mind. Now, to get into numerical modelling, we need a little few definitions. I'm going to come up with a couple here to start with. We've got position, x. Time, t, we're familiar with. Velocity is usually, you'll see it written in equations as dx dt, right? Small change in x, small change in time, that's your velocity. So if I go from here to here, in a short bit of time, you know how fast I went from point A to point B. And if I keep doing that, you know my rough velocity. Now, the other one is acceleration. What's that? Well, that's the change of velocity with respect to time, and you'll see that written in equations as d2x dt squared. The rate of change of velocity, that's how it is. The next one you may not be familiar with is what is the rate of change of acceleration? Anyone know? You may not know. If you don't know, it's called jerk. That's jerk. Now, the one you probably don't know, I was told, was what about the rate of change of jerk, the rate of change of the rate of change of jerk, and the rate of change of the rate of change of jerk. You don't often see these appear, but sometimes the equations, these nutcase things appear. Well, if you don't know what they actually know, they're known as snap, crackle and pop. I love the feeling that an engineer who produced a cereal managed to get through a marketing department terms he used in actually building the machines. And they thought, oh, snap, crackle and pop, that's a brilliant idea. No, it's an engineering term, I got it through. One up for the engineers. So there we are. So you be aware what that gets up. So we'll carry on a little bit. And let's go back to our position and time. Okay? Small change in position, small change in time, we can get it. So let's have a little look at this a little bit further. There we are, small change in x and a small change in time. Whoops, I just moved my mouse a bit. Let's go back a bit. And look, if you think here of how this can work, travelling 60 miles an hour for 1 hour, that's 60 miles an hour. Or 30 miles in half an hour, still 60 miles an hour. 50 miles in a quarter of an hour, 60 miles. 1 mile in 1 minute is 60 miles an hour, or 88 feet per second. These are aspirational figures. I just travelled around the M25. Most of it was at 50. I would have loved to have done 60. But anyway, for those of a more modern bent, you can have kilometres as well. We don't care. But it's not so nice as 88 feet per second as 16.6666 metres per second. I just write 88 feet per second. It works. It's nice. So just think. So if you do 1 kilometre, 1 minute, or 1 second, or whatever, you can work out. Now, we've dealt with this as a constant speed. So let's have a little look. So this is what we've got now. Our small change in x is from where I am, x0, to x1. That's my next point. So I change from here to here. And I took time. T0 is where I start. T1 is where I ended. So we can work that out. Our small change in distance is our endpoint minus our first point, x1 minus x0. Time is t1 minus t0. So the velocity we can actually write as a little equation, which I've given you on the right. Okay? Small change in distance under a small change in time. Okay? So let's have a look. Let's manipulate this equation a little bit. So there's your velocity. Now we bring the time up to the left-hand side. So we got there, velocity times time times that difference, and that will equal what we had on the right side, x1 minus x0, the small difference in time. So if you think, 60 miles an hour, travelled for 1 hour, you've done 60 miles, right? Multiply your time by your speed. That's how it works, okay? So let's move that a little bit further, just move the starting point off to the left-hand side, and we get velocity times the change in time, plus where we started from, gives you where we end. So if I say I'm moving at 5 feet a second, and I start here, and I move for 1 second, I know I'm going to be over here, 5 feet away, and carry on. And if I keep doing this, I'll get to the exit door, and I'll be out. So I think Stephen said I'm not allowed out so before finishing this, and so did Dan, so I've got to stay here. So this is what we use as the fundamentals of working out what we're going to do in our numerical models. So that's our process. We can work out from our starting time and where we position to start with, where we end up. Then if we do that again from where we ended up, the next little step, we get to the next step. As I said, I go from here, our starting point, I end up here, then I know another second, I go a bit further. And this is like Artemisia. You start at one point, you carry on, and you repeat this process. So you use your next step every time you go on, and you work your way down, and on you go, and on you go, and on you go. And this is how you do it. This is what numerical modelling is doing. It's just doing a repetitive calculation all the time. And this model we've got here is just speed, and we've set the speed. And to just give this how we would write this down, we'd write the velocity, it's the time between our previous time step, where we are, plus where we started, equals where we get to. So we're always looking to where we get to. We know where we started, we want to end up with it. And this is what happens in numerical modelling. We take it forward step by step. Computers are good at this. They love doing things step by step. That's their job. That's their job. So there we go. We carry on a little bit further. So bring back that formula, how we work it. But I'm going to cheat a little bit. I want to know our velocity at a particular time. So I'm going to say, at this time, my velocity is 1 metre a second. 1 second away. At this point, at 1 second in, I'm going to go 1.2 metres a second for a second. So now 1.2 further metres away. So I can change my velocity, knowing now the velocity at a particular time, what will happen, okay? Now, I'm going to make it a little bit easier still. I'm going to say the time step is always going to be a fixed time step. Let's say a second, 0.1 of a second, a hundredth of a second, it doesn't really matter. I'm going to fix it. So it makes it a little bit easier. And I'll write that as delta t. We love to use Greek letters because we've run out of the ones in our Arabic, our Roman letters at the present moment, or Latin, and we tend to use Greek ones occasionally just because it makes us look good, I guess. And it's a bit different. And you can actually see in the delta t, if you remember the dx and dt, a delta t, it's the same letter. Okay? So, let's do a little example. Now, there's 2 rules they say in television. Never deal with animals and children. I'm going to go one worse, and don't deal with live examples using a spreadsheet, which is what I'm about to do. Now I'm going to cheat here to show you, because I've shown you an example, but you haven't got the idea of the application yet. Okay? So I'll show you, and it's really quite easy. And once you see how this modelling is done, everything will become clear when they say, yes, when you did a numerical model. You'll be able to say, well, what was your model based upon? How did it work? You'll know how they did the calculations now, but now you want to actually consider how it works. So I'm going to cheat here and say I know what the velocity is. Okay? So just bear with me for a second while I switch screens. Okay. Let me just minimize this for a second. Bring up another screen. Hopefully I've got one here, which I have got there. Let's see if I've got one. And I've got a spreadsheet. Oh, there it is. It's actually there. So that's the velocity. Where is my mouse? There. So here we are. That's my velocity. I've actually printed it out there. That's that little graph I gave you the equation for. And here we go on this. Now, this is going to be very interesting for me to do it. Let's see if I do that. I've done this calculation where on the left-hand side, I'm going to have to change this because I can't sort of, excuse me for a second. Let's just do that and duplicate these so I can see both at the same time. And now I have just hung my machine. Oh, there we are. That's interesting. It's never ever done that. Okay. Okay. Keep changes. There we go. There we go. Okay, that's interesting. Okay, so now I can actually see what I'm doing here. So what we've got here is that delta t I picked as 0.01, a hundredth of a second, let's say. Okay? And I've got 1,000 steps. So that Artemisia, she had 1,000 images deep. She went. Okay? And every step you can see here, I've just added up 0.01. So it goes up, as you can see, bit by bit, 0.01, 0.02, 0.03. And that equation I gave you for velocity, that comes out with this function here, which looks like this. That's it. Now, what I'm going to do on this, if I can remember, is actually show you what the position is, given that figure, and that's my position. So what I've got now on this is, given that this is my velocity curve, for instance, the expansion of the universe, right, how fast it's going, you'll now know how far it's gone. Just using that repetitive, simple equation, time and time and time again, which we've got on the left-hand side. And that is exactly what's here. I've done it in a spreadsheet so you can actually see what's going on. Now, I picked that function of velocity very carefully because I can actually work out really accurately what it should be. And there's the difference between our numerical model here and my real model there. That's the difference between the two. And you can see that there's a slight difference between the two. So you have actually underestimated it by a little bit after 1,000 steps. Okay? So there are inaccuracies which occur because I could actually solve this equation exactly. And what that means by exactly is I could put in the end time, the very end time here, I can put that in and it'll give me an answer. I don't have to do the 1,000 steps. I just put one step in. That's what solving an equation means, is you just give it the final figure, it comes out with the answer. That's the important thing. So this work, and sort of let's say I can actually do this for, let's say, steps. I can go a little bit smaller even. Now there's an advantage going smaller. There we go. We get the first little bit of that curve. There's the first bit of velocity going up there, and there's the distance you actually travel. We get it quite accurately. Okay. Now, that's all well and good. Now, the trouble is, I've done 1,000 iterations, but I've only got in 1 second before I was in 10 seconds. So there's a trade-off. You have small steps, can give you much more accurate answers, but there's a penalty. Time. There's also another penalty. And that is a computer is not 100% accurate. It approximates numbers. They're not exact. You have a 64-bit number. 64 bits isn't a... You can't get pi into 64 bits. You don't need pi. But these errors you have to be very careful of, because sometimes you have some big numbers multiplied by little numbers. And then you have to be a little bit out and you've got a big error. Or you have big numbers minus another big number and a little bit out and you get another error in. So you have to consider very carefully how your computer model is working. The steps you take are important, and you have to actually judge whether or not you're taking too many steps. There are techniques to actually doing this where you actually look at the model and see what results it comes out with. So there we go. So that's a little bit on that one. Now I'm going to take you back to the other screen, hopefully, on this one, if I can get back there. Okay, we've got that one. Now let's go a little bit further. This is where the theoretician comes in. Now I'm a theoretician. I sit there and I work with equations. Okay? And this is where the theoretician and the observer come together with numerical modellings. So let's say, as I said here, what happens if the force you feel depends on how far you're away? The simple analogy, and that is an equation we would write. And that means on the left-hand side, your acceleration, which is force, mass times acceleration is force, is equal to something times your position. Now, the omega squared there, I've put there purposely to make sure it's always positive. Whatever I pick, it's going to be positive. And so it's always pulling you in. So, and where do you see this? You see it on a pendulum. If you pull a pendulum out and let it go, it swings away into the centre, accelerates to the centre, then as it goes past the centre, it starts to slow down. And then it comes back again, and it swings back. And that is how a clock works, the regularity of that pendulum. And this is what that equation describes. It also applies to a spring, a simple spring, etc. This is known as a simple harmonic oscillator. That's how it's actually known, right? I prefer to call it a pendulum. So let's see where we go with this one. Let's see. So this is how you write that equation inside a computer. This is what, and you may notice here, for instance, I'll just show here. See that dt squared underneath? I've brought that up and against the omega squared, and that's where you've got this bit. See that minus omega squared, dt delta t squared? That's those two bits put together. The xi is where we're at. Now, acceleration is a little bit different. I've had to use two previous steps because I need to know how fast I've gone from here to here relative to how fast I've gone from here to here. If I've gone at the same speed, there's no acceleration. If I've gone a little bit less, I must have slowed down. If I've gone a little bit further, I've speeded up. So you use 2 points, or 3 points, or the previous 2 points, to work out your acceleration, and that's how you do this equation. So let's see how that one works. Now, again, let's see if I can do this. Let's escape out of that and see if I can get to my other calculation on another screen. If you just bear with me a second. As I said, don't work with spreadsheets. And we've got another one here. Whoops, there we go. And I'm going to have to bring these screens together so I can actually see them. So sorry about this. Do that. And hopefully it all comes together. Hopefully done that. It's because this is, I've got 2 screens which are split and 2 which aren't. It's a little bit more. And you can see here I've got another one which is a pendulum. And hey presto, I've got a pendulum. same equation, that little finite, and we call them finite difference equations, have given you a pendulum. And now the incredible thing is I now can model a pendulum without, I haven't got one here. I really haven't got one here. So, but I can model the effect of it. And the best bit is I can actually play with this pendulum without actually getting my hands dirty. For instance, let's say the initial position. I'll make it 0.5. It's going to look a little bit different. Hey, that's good. What about if I change the initial velocity and let's say throw it in a little bit or out a little bit? You can see it's now, rather than just falling in, I've thrown it out a little bit from the start and then it's oscillated. And what about that omega factor? Well, if I change that to 0.5, the oscillation period changes a little bit different. And they are the factors. So when you come into doing numerical modelling, you end up with a set of parameters which you start to play around. And this is when they say it fits our model. What they've done is they've looked at the real world and they've actually made it fit that model. You see, so I can play with this. But, and there's a big but here, you have to be careful. You've got to remember the physics you're dealing with. It's the pendulum. If I throw the pendulum too fast, it's not a pendulum anymore, it's a gyroscope. It's going to be spinning around like mad. Or if it's a spring, if I pull it too far, it goes beyond the elastic limit and I've deformed the spring. I've broken it. But this doesn't know that. It doesn't know that at all. So let's play around with it a little bit. Let's say, I know, I want to do a lot of steps. I want to do it quickly. I don't want to do 0.1 of a step. I'll make it faster. We just do every step, every second. It'll be fine. It'll be good. It'll be dandy. It'll be great. And hey, look, I've got the result. But look what the actual result points. This. That's not that at all. Look, if I go back to 0.01 or 0.02 in that case, look, that fits. That's a nice curve. Hey, that's great. But what happens if I make it 1? What's gone on? Well, what's actually happened is I've told this little box here, draw a curve between my dots. Just do it. So it's done it. It's done exactly what I've told it, and it's decided this really fantastic oscillation is what this means. What this means is I've got it all wrong. I've produced rubbish. Because that is no longer an oscillation. This is an equation which is giving you numbers, but it's not actually doing a pendulum. It's actually something else. It's a hallucination. It's fictitious. So this is where you have to be very careful with your models. You've got to actually know. And this is where, if you see this, they say it fits a model. It cannot be a galaxy in this area of the graph. And they'll produce a graph, and they'll have a bit cut through, and it say it can't be in this area. They're wise people, because they know to be in that area, the physics of their equations are wrong. It doesn't apply anymore. So they cannot be in that area because it's like having a planet which is 600 solar masses. You can't have a planet which is 600 solar masses. It's a star. It's not a planet. So you have those cut-offs. And that's what those are all about. They are to let you know that physics has to be taken into account when you do your numerical modelling. There are other things to consider as well. See how it works. Here we go. I've created here what you would actually do in this model. So the red dots are observations, not as good as Stephen's, I'm afraid. It's sort of a little bit more haphazard and saved by the bell. So these are the actual observation times, and as you can see, they're not at every second, a little bit. And these are the observations I've made of something. And let's say it was watching a pendulum. Okay, so I took a pendulum. Every so often I used a little camera, took a photograph, and wasn't so good. Looked at the time of those images, and these are the dots I got. Now, this is where the modelling comes in. I can actually figure out from that pendulum, because I'll say I let it go at the zero velocity, just let it go, and it swings there and back, there and back, there and back. Now, I can work out the characteristic of that one parameter I've got in that model of omega by fitting it. So, here we go. We're going to play a game of lower and higher. I don't think I've been talking away here. You've been all having a nice sit back there. So I've got omega set as 1. Should I go higher or lower? Alan?
Higher.
Higher. 2. You're wrong. John? What figure? 0.25. You're on the right track. Stephen?
Lower, 0.1.
0.1. Again, right. Oh, you're getting good at this. Dan? You knew it was going to be you.
It's going to be higher than 0.15.
0.15. Okay. Right. Getting close. Getting close.
Why don't you use the equation solver and tell it?
Aha! That's why you're all here. You're my equation solver. So
Quite quickly, actually.
it does it quite quickly, I know. But I wanted you to experience what an equation solver does. So the equation solver will actually go through and it will look at the various figures. And I think, if I remember correctly, if I remember about right, what you'll end up is something like 0.133. Something like that. It's maybe a little bit less, 0.1 or something. What happens is you'll hear them saying least squares fit. And what they're doing is working out the difference between the red dot and the blue line above it, each of these figures. And they square the distances because that always gives a positive number, and you add them all up. And the aim is to minimize that error, and that is what a least squares fit is. It actually is a way of making it fit. As you're saying, an equation solver will actually do it. That's what it's doing in the background. That's what it's doing in the background. So you've now got an idea of what's going on, and this is when they say it fits our model. Our model shows that the mass of the two merging black holes, one has a mass of 100 solar masses and one has a 50 solar masses, or whatever. That's what they've done. They've worked the model, they've looked at the oscillation, they've looked at that chirp of LIGO, the theoreticians have come up with the thoughts of how it actually works, the actual mechanism. The numerical modelers have said, right, okay, thank you, we'll run that through and give a model, and we've got 5 parameters to work with, let's say. And this is what they've done. And so then you use your technique of drawing the curves and making them fit. Okay, so we've got a nice little one here. So I'm going to go back to where we were with the little bit of the presentation. Let's change screen again, hope it works. And let's go to this one. And let's go back to from current slide. So that's fine. But let's say you can feel the force, but it's a bit damp. It's sort of like, there we are, it's Valentine's Day went wrong. You could feel the force of love, but it was a bit of a damp squib, it didn't happen, okay? The theoretician comes back with an equation. That's the equation of damping with it. Now you've got 2 parameters, the fundamental of the spring and the damping. Where do you find this? Your shock absorbers in your car. So, if you use this equation, you could actually work out some characteristics as the type of shock absorber to have in your car. Or on the telescope to make sure it doesn't overshoot. So it is actually stabilized a little bit so that it takes up little shocks. All these little things. So the theoretician says, this is the equation you want. The numerical modeler says, great, this is what I'm going to do. And this is how it works out. This is the equation. This is your finite difference equation for that particular model. So now we've got 2 parameters. You've got zeta in there. You've got delta t I've kept fixed. And omega squared. So the 2 things. So we've only got to worry about 2 things in here. We've got 2 parameters. And here, if we go back to our other screen, with a second, if I can get you on that one. Let's go to the next one, a damped one. And this is it. There you go. Using that finite difference equation, which is quite simple, and this has it all in here. That's it. That's the finite difference equation for every degree of time. And now I can play around with what happens if I reduce the damping? Well, you can see it takes longer, it oscillates more. If I increase or decrease the factor, you can see there, let's put zeta up a little bit further. And then you can say, right, okay, we've got still a little bit bounce. So you're in the car and it's bouncing a little bit, okay? But you don't want to bounce like that. You want it to damp. So you can say, okay, let's put that up a little bit. That looks a little bit better. So now the physicist, the theoretician, has given you an equation, right? The numerical modelist says, this is how it looks. And the engineer says, this is what I want. Now I know the two things to build the shock absorber to fit this. And the marketing department says, the Rolls-Royce is the best car ever. It has properly numerically controlled shock absorbers. And this is what goes on in all the time. The beauty of this technique, and this is the true beauty of it, is you can try things out multiple times without the huge expense of engineering. And this is what we have been given in computers and numerical modelling. It is absolutely fantastic. It's a game changer for all of this. And there's a lot more to this. This is just touch the surface of how it actually works. Now, I don't know quite what I've got next, but there we go. Let's go back to this. Right, from current slide. And I think, here we go. There we are. And I think, basically, that's your finite difference equation. You can try this at home. And I'll give you a few seconds for those at home who look at me with their blank eye. Screen grab that, run it into a spreadsheet, as I have done, and you will be able to run that equation at home. I haven't bothered to use any programming languages or anything special. These are all things you can do quite simply in a spreadsheet. You can do it on a calculator. I picked up an email from a chap I knew many years ago called Ivor Stott. And he was a great guy. And it was the letter he was talking about. He was working out his ephemeris of the satellites on his Casio calculator, a programmable calculator. And this was in the 1980s. And how he had spotted a few satellites using his Casio calculator. So, the power of this machine here is quite extraordinary. But you can do this on a calculator. And I remember being, as a school kid, doing similar things to this, working out orbit using finite difference equation. It's nothing special. You deserve a break. This is our cat, Lucky. As you can see, she's the guardian of Lego. Our house is broken. It has too much Lego. I will say that. She rules. We pay the mortgage. She owns the house. And that is it. So there we are. Let's see what we've got. There is one problem, which I haven't touched on yet. There's a new kid on the block. There's a new kid on the block, which is changing the way and how we interact with it. And it's almost making it work. RL, reinforcement learning. Not a comic character which someone knows about. It's actually reinforcement learning. This is where AI has come in, and it's a new way. I'll give you examples here because it will take a long time to actually go through it, but I'll just explain it in simple principle terms. Consider a marble rolling down a gully or down the stairs here. What you do is, with the reinforcement learning, you look at where it is, the marble is, and you give it some physics, saying, I want to fall downhill a little bit. So it falls downhill a little bit. AI uses this, and when AI gets it wrong and it pushes it back up the hill, the reinforcement learning says, naughty AI, I'm going downhill. And AI goes, oh, sorry about that. I'm really sorry. I won't do it again. And the reinforcement learning says, you better not, because every time you get it wrong, I'm going to punish you. And you get this reward and punishment going on within reinforcement learning. So that every time it goes wrong, the AI model says, I don't do that. And it learns that every time it makes a mistake, like a small child getting up and lifting up both feet and falling flat on its face, it learns that this is not a good idea. And suddenly thinks, okay, well, I'll better keep one foot on the ground would be a good idea. So it learns that. So they think, okay, that's a good idea, I'll move the other foot. Then it thinks, well, actually, if I put both hands on the ground as well, that'd be good. But your physics model says, no, you're not efficient. You're not efficient. And this is what's going into the reinforcement learning. We're now adding efficiencies. We're adding the physics into artificial intelligence. Remember, it is artificial and it's not intelligent. But what you're doing is trying to give it a probability. And that's what sits behind AI. It's a string of probabilities. They're known as weights and biases. And this reinforcement learning you get, which is referred to as this and other terms, is an idea of bringing physics into it. And we're at the start of a very exciting episode of where this is. And where it comes in, where numerical modelling, as we did have, had a problem, was things such as turbulence. Turbulence was an absolute nightmare to compute because you have structures on such small scales. Your time steps and your periods of space you had to work in got really, really small. And those time steps took time. A lot of computer time. And computer time is expensive. And computer time means you cannot do very many models. If you can't do very many models, you can't get the results out you need to actually compare if your original model is correct. So you have this continuous fight between wanting to get models out and trying to keep them accurate. Small time steps generally mean more accurate, but you haven't got the time to do that. You need to get the results out. And this is very much a case where students are actually against the wire, and researchers, all researchers, postdocs, lecturers, professors, are all against the wire. They have finite time in which to do these things. Yes, they're fantastic computers now. You know, originally like the Cray 1, look it up, the original supercomputer. What was its speed? 80 megahertz. 80 megahertz. I think this is running at 4 gigahertz. All right? Or thereabouts.
Yeah,
and
the laptop is doing about 100 gigaflops, whereas the first Cray is about 18 megaflops.
yeah, yeah.
And then if you're running multiple cores, because I use Cadence at work, I'm a machine designer.
Yeah.
And we sold our nets in Spice are running 100,000 nodes.
Yeah.
And we're running on. They're not in the physics world actually in Cadence, which is actually you can only run 256 cores, whereas in the physics world you can run with GPUs.
Yeah. Like I've got a GPU in here which is over 3,000 cores.
Yeah.
I've got 24 cores running on the CPU. Yeah. And it's amazing. The thing about the Cray 1, where it actually created a difference, is up to that point, you had an instruction which said, right, add 2 registers together, multiply 2 registers together. And it was always one register with another register. Copy that register into memory. Where Cray changed it was he was able to do several. We've got 8 or 80 numbers, and we all add them up to 80 different numbers in one hit. And that's where you got the speed up from it. Now, Seymour Cray said he wasn't a great electronic engineer. He was a very good plumber. And the reason for that is the more you force that through, the hotter the machine became. And the big idea was to keep it cool. And I remember speaking to an engineer who worked on setting up Cray 1s. And they were notorious. What you actually did, because it was breaking edge technology, I'm sorry we've gone a bit left field here, but it's worthwhile mentioning it. They actually, at that stage, used to run wires from the Cray 1 out into a corridor and measure the length with an oscilloscope to see how long light would take to travel along that length of wire. They would then cut it to the right length to get the right signal delay. and plug it back in. And they used to do it. And if they left a test card in, because you have this huge wall and you've got all these circuits in, but you can't get your oscilloscope test probes in it, so you just put a little external thing to plug on so you could actually get to it from above and below. If you left one of those in, that extra light time, because it was such a delicate machine, would stop it booting. We take it for granted. My watch has more power than a Cray 1, and it's mind-blowing. But that step of that Cray 1 changed everything. Queen Mary College had DAP, which is a distributed array processor, which was a similar idea. I think it had 64 cores running in it as well. So all of these things, the computing power, now that we have memory in abundance, we have processors in abundance, we can now do these things like reinforced learning. Before we just couldn't. And this is why we've got a new kid on the block. But there we go. I'm going to leave you with that. I'm going to thank you all for bearing with me in this talk. I hope you have learned something. Try these things at home, for those on YouTube or Zoom, and give it a go. It's nothing to harm. You won't hurt anything. You won't crash a car because the damping is too little. You won't have a pendulum flying off and hitting someone in the eye. It's all done in the safety of your own CPU. Thank you.
That I picked up just recently. This is a hard drive which would save 205 megabytes.
205?
Yes.
How much is that?
Yes.
Wow.
Yeah. Fairly costly.
Yeah.
Right, does anybody have any questions that they'd like to put to Quentin?
Oh, yeah.
Yes. One
There
up
we
there. Okay, so we just hold on till we get the microphone to you.
That is very impressive. I don't know. It's a Model 2 Series 4000C. I
Yes,
guess it's IBM.
1961.
But what's the kind of the practical application of that for kind of astrophysics? What type of things would they model and want to prove?
Practically everything. Seriously, practically everything. Whether it's the evolution of a galaxy, how it works, when it comes to supernova, when it works, the eclipsing binaries, you working out the mass of the planet going past. You get the eclipse, you get the dip in there. Those oscillations, all of those figures, those observations, you would use, and you'd run one of these finite difference models, in essence, against it, and figure out the parameters. This isn't the only way it's done, but this is one of many ways it can be done. It's like art, as I showed you. You have various versions of art. You could recognize them. And that sort of boiling pot of different techniques get used. But what you use in this is you actually take your observations, as we did with my made-up oscillation, and you fit it, and that gives us a characteristic. When we know what we're talking about, it's, for instance, just trying to think of some of John's examples earlier, sort of like the Wolf-Rayet star, where there's double star in there, where it's actually pushing out the planetary nebula. You're actually modelling the pressure which is actually going out there, the gas, the mass, all of these little bits and pieces. That's the practical application. Engineering really has it. I can actually show it here, where you actually use it to design aircraft. It's very much safer to design an aircraft in the CPU than saying, John, would you mind taking this one out? We don't know if it's going to work, but we've decided we want to change the wing configuration. We're going to have them big wings on the right and small wings on the left because it parks better. So you could do that, but I think our test pilot might object. But we might have a few ones. So yeah, there's a lot of practical application, and that's a very good question to ask.
Any others in the room? Do you have any online?
Yes, we do.
Oh, right,
Okay.
good. Hello, online.
I was going to say, do remember you're in Hatfield, the home of de Havilland's.
Yes, that's right. Not far away.
Okay,
far.
one's on Zoom.
Yeah.
So Peter Jenkins asks, he has two questions. Thanks
Peter.
for the thought-provoking lecture. How do you share a new theoretical model with others for peer review to get their feedback on whether you've got it right or what adjustments may be needed?
That's a very good one. Sort of like, obviously you've got archive where you could submit things if you've got other people to help you with that actual submission. Generally, most people you can contact at the universities, you know, if they're worth their salt, they will actually come back and actually check you with your theoretical model. If it's really harebrained, don't be surprised if you said it's harebrained. I have seen some fantastic theories, and they, you know, unfortunately the physics just don't work. And the biggest problem is everyone has the right to try these things out, etc., and it's very incumbent on the academics, etc., to take these on board, because somewhere amongst all of them, and there are countless stories of where someone has come up with something, especially in the world of mathematics, where they have actually proved a theorem which people thought wasn't possible, or they come up with a new technique. I'm trying to think. Hardy. Oh gosh, I can't remember his name. But yeah, you'll find a few people where that actually has happened, and it is very important. The thing is, you come up with a model. One thing you could actually do here, if you think of your theorem and it's a differential equation, follow some of the guidelines I've given here this evening and write it out in a spreadsheet. Just follow it through like Artemisia did, a painting of a painting of a painting of a painting of a painting. You can actually work out whether that's actually doing what you think it's doing. It's not that difficult to actually do. And there are techniques. I think Python would be amongst them, which has libraries for this. I've only dealt with everything on the straight line. It gets much more interesting when you get into volumes and surfaces. And like Fourier did the original analysis, Fourier series, which is where you break things down into frequencies, was actually done for heat transfer on a plate. It's fascinating. That's going back to your question, is where the actual theory gave a result which revolutionized everything. So never be backward in coming forward with an idea. Just speak to someone. Run it past your peers or someone else to see what they think. And you know, always remember the feedback is there to help. If it's not to help, then go to find someone else who will help you. So there we go.
Peter also asked a second question. COVID predictions gave computer modelling a very bad name. What were the biggest problems, e.g. lack of time for peer review or no experience of the rules influencing the progression of the disease?
Which ones were that? Which was the problem to start with? I missed it.
COVID predictions, COVID. Yeah.
I think at that stage it's a very interesting thing because little was known. And I think my wife is far better placed than I am. Would you like to say something, Liz, on that at all? No. She says no. But would you like to say something?
I'm happy to.
Yeah, Liz, if you'd like to add. So she actually works for Springer Nature. I'll just introduce my wife, Liz. She works for Springer Nature and actually works on peer-reviewed journals. So we have some very intriguing conversations at night. So there we are, Liz, you're on camera.
Oh dear. My argument would be that the original COVID predictions weren't actually that bad. It's what the governments did with them. So the scientific predictions were pretty fair, but the government predictions from them were inclined to cherry pick. You can't throw out the data that doesn't say what you want and then complain that your models aren't good. If you throw out your data or you don't follow the instructions, let's model based on complete lockdown very early and then wonder why we didn't get that outcome because we didn't lock down for an extra couple of weeks. To a government, 2 weeks isn't long. To a virus, 2 weeks is a very long time, yeah. Particularly an RNA virus. And that goes with the whole thing about understand the physics. In this case, understand the biology and the physics. Yeah. It's not just pure biology, and there was some meteorological aspects, travel aspects, things that were pure mathematical modelling. And there were a lot of people trying to do it that really weren't mathematicians as well. Yeah.
I'd sort of like to add on to that. This is and Liz is pointing on a very salient point on this, is that the models I've given you are very simple models. I've cherry-picked them, and I don't deny that, because we needed to get something. You get to a situation where the models are very, very difficult. The biological being, us, we just cannot model. I wish we could. If we could, it would be fantastic, but it just isn't possible at this present moment. So this is where you have to, this is the other danger which comes in from theoreticians, people like myself, is you have to sometimes make assumptions of what is important against what isn't important. And I remember, because as training, I was a pure mathematician, and my first meeting with my supervisor, he wrote out this long equation. And I looked at it and I said, right, fine. And he said, sort of describe this equation. So I wrote out the furthermore and sort of added all the time. He said, well, we can throw out this bit, this bit, this bit. And I was sort of aghast. Equations are sacrosanct. You cannot throw things away. You know, 1 + 1 is 2. You can't make it 0.9. It's got to be 2. And he said, no, we get rid of it. And I sort of like, you realise after a while that there is a justification for this, because most systems are what are known as dissipative. In other words, things which happen have a lesser effect later on. As Liz was pointing out, for a virus, that's not necessarily the case. It can actually grow, and it can grow exponentially. So you have to be very careful. You've got to know the science. And then we get into the situation which I'm not going to get into, is the politics of it all. So you've got to be very careful. And I will say, you do get people presenting papers, and I have been at lectures where you have people presenting things, and they've picked the results which back up their things. And papers do try to get through peer review, where people have picked things. And this is why we have peer review, to try and stop that cherry picking. But this is way beyond reinforcement learning and numerical modelling, so I apologise. But again, you're a tough crowd. I love it. Come on! Ask more questions.
Any more in the room?
Yeah.
Was that style of modelling what was used for the determination of the first gravitational wave collapse of 2 black holes?
Right. I wasn't involved in the modelling of that at all, so I will admit on that. But the thing is, you know the Einstein equations, right? The general relativity equations, so you can actually work on that. And from that, you can actually work out the orbital mechanics. And then you can work out how space-time is manipulated by 2 colliding bodies. And you get this fantastic chirp, because it's like 2 balls running, and as they speed up as they get together, and then you get this enormous bang as they hit, and they merge into each other. And LIGO is just, I just don't comprehend how it works. It is so amazing, because you're dealing with something which is several kilometres long, and it's got to be accurate to within the width of a proton. It is just, I just don't get it. And the next generation, I think the 3rd generation, this is a very interesting one. RAS meeting, I think one before last. This is an interesting one. The 3rd generation of LIGO, and this is going to be really intriguing, is something like 2 orders of magnitude more sensitive. In other words, 100 times more sensitive. The problem is, and they don't know how to handle this, and they're using AI models at the present moment to try and make this work, is to say, what will happen if we see mergers happening continuously, which is likely to be the case now. They thought a merger would be 1 in a century, and now they're just happening all the time. And now they're thinking, well, if we're really sensitive, we're going to be seeing these all the time, and they're actually going to sit on top of each other. So while one's chirping, the other one's starting to chirp, and the other one echoes that chirp. How, with all this very, very, very fine signals, and we're talking really, really small signals here, do you disseminate which is which one? And you actually pick it out, because there's a lot of noise, and inside that you've got this little signal which you're looking for. And they are really concerned that they can come up with the techniques to actually do this. And again, going back to your sort of question, this is where the actual application comes in, because the numbers coming out of the science are so phenomenal, the theoreticians and the modelers are having a problem to keep up with it, because it's almost an arms race between who can beat each other. I can come up with lots and lots of stories of this, but it is a case that going back to your original question, again, you break down your equations of motion into as small as number of parameters as you can, and then you do your modelling, you create it, and then you adjust those parameters a little by little until you get the best fit. And this is why you end up with ranges of, it could be a mass of between 10 and 15, or it could be 30, 100, whatever, or it could be two other objects, because you get such a good fit between the two different models, you can't actually decide. It is actually very good, but yeah, it's a case of the model fitting after you've done the numerical modelling. Okay.
Okay. Any more online?
Any more?
No. Okay.
They've all gone for their cup of tea.
I have a sort of indirect question. You showed the image of the painting of the Scream.
Yes.
Do you know why the sky was orange rather than blue?
I think I'm going to find out.
At the time it was painted, it was shortly after the Krakatoa eruption, or I should say explosion, which changed the colour of the skies all the way around the world.
Of course, that's right.
So there we go.
There we go. See, everyone learns from everyone.
An astronomical connection.
There we go.
as it
Brilliant.
were,
Thank you very much,
almost.
Jerry.
Right, if there are no more, then I'm sure you'd like to show your appreciation for tonight's presentation from Quentin. Thank you very much.
Thank you. Thank you, Jerry. Thank you for your invitation. Thank you very, very much.
And I'll hand you back to Alan.
Oh, thank you very much indeed, Quentin and
Thank you,
Jerry.
Alan.
Absolutely superb. Okay, just a few announcements. 2 weeks' time, Haggas have got a meeting here at 8 o'clock. It's an open meeting, so if you've got questions about astrophotography, that will be a good one. And actually, on the same evening, just before the Haggas meeting, the Institute of Physics have a talk, Quantum-Enabled Network Radar, Fact or Fiction. So there you go. Do you know? Well, if you want to find out about that, do come along. That's at 7 o'clock, so you can go from one meeting to another. What a night out for you. On the 7th of March, it's the next Bayfordbury Open evening, last one of this season. So if you want to come along to that, bring along a telescope, and let's hope that the rain gods keep away this time. Our next meeting is here on the 12th of March, when we've got Mike Fawkes coming along to talk about eclipses, which is pretty convenient because on the 29th of March there's a partial eclipse, and it's a Saturday, and the eclipse happens between about 10 o'clock in the morning and 12 o'clock. Couldn't be more convenient, could it? What we're going to do is set up a display in the grounds of Hertford Castle, where we had the Dark Skies event, and again we would like some volunteers to come along to talk to the public, show simple demonstrations, show the safe ways to have a look at it, and let's hope it's going to be a lovely sunny day. We'll give more notice about that later. And on the 15th of March, just a few days after our next meeting here, on the 15th of March, Bengio Primary School are doing an astronomy evening. At the moment, they've got it planned from 6 o'clock to 8 o'clock. I had a word with them earlier to say, you do realise it's going to be quite light at 6 o'clock, so they are looking to move it back to perhaps 6:30 or a little later. So that's Friday the 15th of March, and with a bit of luck, if the sky is clear, not only will we be able to see a few of the stars and planets, but the International Space Station is due to fly over, so there ought to be something good there for the children. But most of all, they do want to look through excuse me, they do want to look through telescopes. So that's enough from me. I'd like to say thank you to everybody who came along this evening. I'd like to thank the technical team and all the admin teams that have put it all together, and of course, most of all, our guest speaker. Do have a safe journey on the way home, and I look forward to seeing you in the near future. Thank you and good night.